Hello and welcome to section 7.4. Today we're going to look at what we call partial fractions. Now when dealing with partial fractions, we actually have a goal that we want to keep in mind. And this goal is going to be to write a rational expression. And remember, a rational expression is just a fraction of polynomials. So we want to write a rational expression as the sum, which could also be a difference, of two or more simpler rational expressions. So in order to do this, what we've got is we have this right here. We would be given something like this, and this is what we're going to call our partial fraction. And I'm just going to write PF decomposition. So this is what we're going to be decomposing into simpler pieces. And then each one of these here are going to be the parts or the partial fractions of that partial fraction decomposition. So if you were to go back and double check your work, if you took these two fractions, added them together, you would in fact get this if you've done everything correctly. In order to do a decomposition of a partial fraction, the first thing we're going to do, and this isn't always necessary, but you must check for it very first thing, is you have to divide if your fraction is improper. So in other words, if your numerator has a higher degree than the denominator, then we must divide it. So when you divide that out, what you're going to end up with is some polynomial, and then we're going to end up with another rational expression that will be a fraction of the original one. Okay, because you can only do partial fraction decompositions on fractional pieces. You can't do it on something that will divide out nicely. Once we've got a lower degree in the numerator than in the denominator, then what we're going to do is we're going to look at steps 2 through 4. So the first thing we're going to do is we're going to factor the denominator, and we're going to do this completely. In other words, if we completely factor, so completely factor the denominator, each factor will not be able to be reduced if it's completely factored. Ideally, we would like to get linear factors, but sometimes that doesn't always happen, so we will we'll have to have quadratic factors or something else. For each linear factor that we encounter or come up with, we're going to have something of the form a sub 1 divided by that linear factor, or px plus q, and we're going to add it to a sub 2 divided by px plus q squared plus, and we're going to continue to do this until we reach the repeated factor, or the degree of the repeated factor. So then I'm going to put a sub m divided by px plus q to the mth power. Now one thing I want to kind of make sure that you understand is when we're talking linear factors, we're talking about what is inside of this set of parentheses. So notice that anytime I have something like ax plus b, or in this case px plus q, I have a linear factor because this is a degree of 1. Now even when I go right here to this step, I have a square function here, but this is still a linear factor, because this right here, if I were to graph just this factor alone, it's a first degree polynomial, this would give me a linear line. So this is still a linear factor, even though it's being squared right here. And then last but not least, we have what we call quadratic factors. So for each quadratic factor, we're going to include a bx, and we'll say b sub 1x plus c sub 1 over the quadratic factor, which would be ax squared plus bx plus c. And then we're going to add that to our b sub 2x plus c sub 2 divided by ax squared plus bx plus c, all the way down until we get the the repeated quantity of that quadratic factor. So we'll say plus b sub m x plus c sub m divided by the quantity, and this here should have been the quantity as well, squared, ax squared plus bx plus c to the power of m. Now I realize that some of this might not make sense right now, but let's look at a few examples here. So for example 1, we want to write the partial fraction decomposition of x plus 8 divided by the quantity of x squared plus 6x plus 8. Now to start out with, my degree of my numerator is less than the degree of the denominator, so I do not have to divide out. So I'm just going to go ahead and start out by factoring this denominator. And when I factor it, I end up with x plus 4 times x plus 2. Now if you notice, both factors are linear factors. So when we have linear factors, this actually makes it easier for us. So what we're going to do is we are going to rewrite. I have x plus 8 divided by x squared plus 6x plus 8 equals, and I'm going to place an a over my x plus 4, and then I'm going to add that to b over my other factor, which would become x plus 2. And now what I'm going to do is I'm going to solve for a and b. And to do that, I want to clear out my denominators. So if I take this whole thing and I multiply by my denominator, and in this case I'm going to multiply it by the x plus 4 times the x plus 2. And remember, that's going to cancel this out because these right here are the factors of this. So when I multiply everything by that, my x plus 4 and x plus 2s are going to cancel out this denominator here, and that's going to leave us with x plus 8 equals, when I multiply this right here by my a term, my x plus 4s are going to cancel, and that's going to leave us with a times x plus 2. And then I'm going to distribute that common denominator onto my b term. Well, the x plus 2s are going to cancel out, and I'm going to be left with the x plus 4 term. So now when we're dealing with linear denominators, okay, I think the easiest way in this case is I'm going to go ahead and just use a substitution method. And I see that if I call x, or if I say that x is equal to like a -2, what that's going to allow me to do is that's going to allow me to cancel out my whole a term, because that's going to make this piece 0, and a times 0 is 0. So what that does then is that leaves me with just a value of b to solve for. So if I set x equal to -2, I end up with -2 plus 8 equals a times -2 plus 2 plus b times -2 plus 4, or I end up with 6 equals 0 plus 2b, and now when I go to solve for b, I see that b is equal to 3. So I've accomplished one of my goals. Now I'm going to do the same thing, except I'm going to set x equal to a -4 so that I can cancel out my b term. So then we have -4 plus 8 equals a times -4 plus 2 plus b, and that's going to be 0, because -4 plus 4 is 0. Or I have 4 equals a times -4 plus 2 is going to give me a -2, so I really have a -2a, which tells me that a then is equal to a -2. So to complete my problem, and you have to do this, okay, because when you factor, you might have x plus 2 first instead of x plus 4, so you have to go back and substitute what your a and b values are. So in this case, a was a -2, so I'm going to rewrite this as the partial fraction decomposition of x plus 8 times x squared plus 6x plus 8, and say that that is equal to a -2 divided by x plus 4 plus b, which was 3, divided by x plus 2. And this here would be my partial fraction decomposition. And again, if you were to go and add these two together, get your common denominators, you will end up with this right here. Example 2 says to write the partial fraction decomposition of 3x squared minus x plus 5 divided by x cubed minus 2x squared plus x. So again, the first thing we're going to do is we're going to check and make sure this has a lower degree than the denominator here. So I don't have to divide, but I do have to factor that denominator. And to factor my denominator, this is going to give me x times x squared minus 2x plus 1. And I can actually break that up into x times x minus 1 times another x minus 1, or an x minus 1 squared. Well, when you look at your factors, this is a linear factor, this is a linear factor. So when I go to do my partial fraction decomposition, I can write that as, I'm just going to go with the first factor, which is x, so I'm going to put a divided by x plus, now I have a linear factor here that is being squared. So I must first write that linear factor as b divided by x minus 1 to the first power. And then in the next step, I'm actually going to go plus c because it's still a linear factor, x minus 1, and then this quantity is being squared. We're again going to clear out our denominators. So we're going to multiply everything by our least common denominator. And in this case, the least common denominator was x times the quantity of x minus 1 squared. So when I multiply this first piece by that common denominator, I'm going to be left with 3x squared minus x plus 5 equals, I'm going to have my x's are going to cancel, and I'll be left with x minus 1 squared plus b. Now I'm going to have, actually, let me erase that. We're going to have an x left over. So bx, and I'm still going to have 1x minus 1 left. And then I'm going to add that to c, and I'm going to have an x left, but my x minus 1, the quantity squared, is all going to cancel. So now what I'm going to do is I'm going to see, because again I have linear factors, so this should work out pretty nice. If I set x equal to 1, I see that I'm going to be able to cancel out my a term and my b term. So I end up with 3 minus 1 plus 5 equals a times 0 squared plus b times 0 plus c times 1, or c. So in other words, c then is going to equal 3 minus 1, which is 2, plus 5, or 7. So I can go ahead and replace this c value with a 7. And now if I want to go ahead, I got to look and see what can I can't use 1 anymore, but I notice right here that if I plug in a 0 for x, that's going to make this one go away and this term go away, so then I can then solve for a. So when x equals 0, I end up with 0 minus 0 plus 5 equals a times a negative 1 squared plus 0 plus 0, or a equals 5. So again, I can come up here and say that, a is equal to 5. And then I have to solve for b. At this point in time, I've solved for a and I've solved for c. There's nothing that I can plug in because 0 and 1 are going to take care of my a and c terms, but I have an x and an x minus 1 in both of these. So now the only thing I'm going to do is I'm going to try to pick a number that's going to make this work out like a nice number. So in this case, I'm going to pick the value of x equals 2, because 2 minus 1 is going to give me 1. So now if I go and I plug a 2 in for that equation, I end up with 3 times 2 squared minus 2 plus 5 equals my a value, which we said was 5, times 2 minus 1 squared plus, I still don't know what b is, x is 2, and I'm going to end up with 2 minus 1 in the parenthesis. And then I have plus c, which was 7, times 2. So this gives me 3 times 2 squared, or 3 times 4 is 12 minus 2 plus 5 equals 5 times 2 minus 1, which is 1 squared is still 1, plus 2b plus 14. So if I simplify this, I have 15 equals 19 plus 2b. And if I move my 19 over and divide by 2, then I end up with b equals a negative 2. So now I can go back up and put in a negative 2 for my b. So I end up with 5 divided by x plus a negative 2 divided by x minus 1 plus 7 divided by x, or the quantity of x minus 1 squared. And that will conclude this example. Now for example 3, it says to write the partial fraction decomposition of 5x squared minus x plus 27 divided by x cubed plus 9x. Again, I'm going to start out by doing the long division, or checking to see if I have to do the division. I have 5x squared and an x cubed. The degree of my numerator is less than the denominator, so I do not have to do division. But that doesn't mean, or that does mean I should say, that I do still have to factor out my denominator. So when I factor that, I end up with x times the quantity of x squared plus 9. I can't reduce the factor of x, and I can't reduce x squared plus 9. So when I go to rewrite this, I have a linear factor and a quadratic factor. So I'll say 5x squared minus x plus 27 divided by x cubed plus 9x is equal to a divided by my linear factor x. And now, because I have a quadratic factor here, I am going to have to write bx plus c in the numerator now, because that's going to indicate that I have a quadratic equation in the denominator. So then I have x squared plus 9. So now my process is still the same as what it has been all along. I'm going to go through and I'm going to multiply the whole thing by the common denominator, which is x times x squared plus 9. When I distribute that, I'm going to be left with 5x squared minus x plus 27 is equal to, my x's will cancel out with the a, so I have a times the quantity of x squared plus 9, plus I'm going to have bx plus c, and I would highly suggest that you put that in parentheses so that you will remember to FOIL if you need to. And then my x squared plus 9s are going to cancel, but I am going to be multiplying that by x. So now when I go to simplify, I have 5x squared minus x plus 27 equals ax squared plus 9a plus bx squared plus cx. And this is where things get a little bit different. My 5x squared minus x plus 27 stays the same, but I'm going to group my like terms together. So in this case, I see I have an x squared term and an x squared term. So I'm going to write this as a plus b times x squared plus I have a cx term, and then I have a constant, or 9a. So now, two polynomials, which is what I have here, are equal if and only if the coefficients of the like terms are equal. So what that means then is my coefficient is 5 on my x squared term. 5 has to equal a plus b. So I am now going to rewrite this as a plus b equals 5. I see that my x term is going to mean that c is equal to a negative 1 from this right here. And my constant term I have 9a is going to equal the constant of 27. Well, in this case, it's going to be really easy to figure out what a is just by using this right here. C is already solved for me, so I still have to, C is equal to -1. A then is going to equal 27 divided by 9, or 3, and that tells me then that B is going to equal 3 plus B is 5, so B then is equal to 2. So A, B, and C are here, so if we want, we can kind of scroll up and say that A is equal to 3, B is equal to 2, and C is a -1. And our final example says to write the partial fraction decomposition of 6x cubed plus 16x divided by x squared plus 3, the quantity squared. Again, I'm initially going to check and make sure that the degree of the numerator is less than the degree of the denominator. And if we were to square this, this would become an x to the 4th, so it is. So now I'm going to factor. Well, my factors are going to give me x squared plus 3 and x squared plus 3. So when I rewrite this, I end up with 6x cubed plus 16x divided by x squared plus 3, the quantity squared. This is going to give me, now remember, I have to do, both of these are quadratic factors. So I'm going to have to go ax plus b, and I'm going to have to divide it by the first factor to the first power. So x squared plus 3, and if you want, you can put parentheses around it and put it to the first. And then I'm going to add that to my second factor, which is being squared, and I'm going to have to square the denominator of the second factor, but then I'm going to have to go cx plus d because it's another quadratic factor. So now I have x squared plus 3, the quantity squared. And my process is again the same. I'm going to take all of this, multiply it by my common denominator of x squared plus 3, the quantity squared. That gives us 6x cubed plus 16x equals ax plus b, and only one of those are going to cancel, so then I have x squared plus 3, and I'm going to add that to cx plus d. So now I'm going to simplify, and to simplify, I end up with 6x cubed plus 16x equals, I have to FOIL these two, which is going to give me ax cubed plus 3ax plus bx squared plus 3b, and I'm still going to be adding the cx and the d. So again, I'm going to go through and I'm going to group my like terms. So 6x cubed plus 16x, equals, I'm going to have just my ax cubed term. My x squared terms are just bx squared. My x terms are going to be 3a plus c, and then for my constant terms, I have a 3b and a d, so I'm going to go plus 3b plus d, and that should be 3. Okay, so now I'm going to equate everything. For my x cubed terms, I have 6 equals a. Then for my x squared terms, I don't have any x squared terms over here, so I'm just going to say 0 equals b. And for my x terms, which I didn't write in my x up here, this should have an x. I'm going to end up with 16 is equal to 3a plus c. And for my constants, I don't have any constants over here, so I'm going to say 0 equals 3b plus d. So based upon all of this information right here, I know that a equals 6, V equals 0. And then I can use like this equation right here and say that 16 is equal to 3 times 6 plus C, or C then is equal to a negative 2. And D, I can use this equation and say that 0 equals 3 times 0 plus D, or D equals 0. So to simplify this, I'm going to go back up and I'm going to plug in a 6 for this A. I have no B term because that's 0. C is going to be a negative 2, and D is also 0. So that would be my final answer then. And it's at this point we're going to stop. And I hope you guys have a good night, and I'll see you in class tomorrow. Thanks.